In this video, I will go over this finance research paper called A One-Factor Model of Interest Rates and Its Application to Treasury Bond Options by authors Black, Derman, and Toy. It was published in the Financial Analyst Journal, January-February 1990, Volume 46, Number 1. And it was developed by Black, Derman, and Toy when they were at Goldman Sachs in the 1980s. So we can get the paper from this link, and it is also provided to the class on Canvas. So the questions that we are going to go over are, what is the big picture this paper was trying to address? What motivated the authors? Why did they write this paper? How did this paper impact the academic discipline? And more importantly, what is the methodology that they used in this paper? So coming up with their idea involved a lot of time put in. That was a challenge. And secondly, the authors had to select what methodology to use and how to implement it. And 5, how did other researchers expand on this paper's contribution? So the reason why we're looking at why other researchers are expanding is because it gives us some ideas on how we could expand on a paper like this. And finally, 6, is there anything left in the area still unanswered today? So in this last question, we're trying to figure out if we ourselves could have some ideas, and maybe we could eventually come up with our own paper and publish it, etc. So let's go over these 6 questions one at a time. 1, what was the big picture the question was trying to address? The big picture in this paper tries to address 3 research questions. 1, can we find a simple, fast, and accurate way to value interest rate sensitive securities? 2, can we then find a simple, fast, and accurate way to value the options on the underlying securities? And 3, can we also determine the option hedge ratios for our position? So 2, what motivated the authors? So first, the authors were motivated by the need for simplicity. The authors noted that existing interest rate models were too complex to implement, so the authors wanted to take a new approach and propose a one-factor model, one where the short rate, the one-period interest rate, would drive all security prices. Next, the authors were motivated by the need for speed. They noticed that existing models were too slow to implement, so they wanted to create something that would provide traders with fast pricing tools. And finally, the authors were motivated by the need for accuracy. Existing models often fail to align with market data, so the authors wanted to use observable inputs like current market yields and volatilities. 3, how did this paper impact the academic discipline? So previous literature looked at single-factor models, pricing with binomial trees, valuation by discounting using interest rates, the mean reverting nature of interest rates, log normal uncertainty, interest rate volatility, calibration, and term structures. Authors of this prior research include Vasicek, Cox-Ingersoll-Ross or CIR, Cox-Ross-Rubinstein or CRR, Dothan-Black, Holy, Black-Scholes, Harrison-Krebs, and Jamshidian. But these models did not incorporate all these elements together. By contrast, the Black-Derman-Toy model, or BDT model, which is the model we have here, incorporated all the elements together in a single-factor model. It was a breakthrough in that it was the first model to combine mean reversion of short rates with a log normal distribution, and it could be calibrated exactly to fit the market term structure of current Treasury yield curve and the implied interest rate volatilities. So this paper has about 1,560 citations according to Google Scholar, and at least 8 papers, in reality probably many more, followed, but we found 8. And finally, researchers and practitioners often use the BDT model as a benchmark or a starting point for more complex models. It's particularly relevant in calibration to real-world data, such as historical yield curves and volatility structures. So, what was the methodological contribution of the paper? The authors wanted to find a simple, fast way to price bonds and bond options. So to be simple, the authors wanted to depend only on a single factor, the short rate. To be fast, the authors decided to use interpolation to calibrate their calculations to market data, and they decided to use interpolation instead of creating a very large model. And finally, to be accurate, the authors wanted to align their calculations to existing market term structures. So this is all to say that this paper developed a methodology to construct a tree of possible future short rates in order to value interest rate sensitive securities, value the corresponding options, and determine the option hedge ratios. So what is our hypothesis in this paper? We know a bond has a known price at maturity, no matter what short rate prevails. We know we can find possible bond prices prior to maturity by discounting the price at maturity backward by possible short rates. And we know that looking at the market term structure composed of the current yield curve and implied volatilities, we have real and observable market data there. So our hypothesis in this paper is a single factor model which depends only on the short rate in alignment with market data, can accurately value bonds, the corresponding options, and the appropriate option hedge ratios. Is there evidence in the data to support the hypothesis of this paper? The authors found that the short trees, which resulted from matching their model to the market term structure, enabled the creation of other trees that could accurately value treasuries and their corresponding options. The authors found that interpolating across these trees gave results that were both accurate and fast. Once model values were matched to the term structure, options could be valued in seconds. When the authors increased the number of factors in the model, the results improved. However, the multi-factor model was much harder to think about and work with. It also took much more computer time. Thus, the authors found that it pays to work with different single-factor models before moving on to a multi-factor model. So basically, the authors found from working with this model that the results were good enough to prove their hypothesis. Now we will explain the model itself. The model is based on 4 assumptions. First, changes in all bond yields are perfectly correlated. Next, expected returns on all securities over one period are equal. Then short rates at any time are log normally distributed. And finally, there are no taxes or trading costs. So this is the valuation formula that we use to find prices one time period from now. This is a one-step tree. In our demo, one time period equals 1 year. We know today's price S here. The model assumes that over the next year, the price will move up or down with equal probability. It will either go up to S sub U or it will go down to S sub D. And the halves you see denote the probabilities. So thus, the expected price 1 year from now is half the sum of both prices. Then, because the model assumes all expected returns are equal, the expected return is the future price over today's price. And then finally, since we know today's short rate R, we can discount the future price at R to get today's price. So this is the future price, this is the discounting, and this is today's price. Next, we can use the valuation formula to get today's prices using future prices in a 2-step tree. Say we're looking at a 2-year, 0 coupon Treasury bond. We have 2 pieces of known information. In 2 years, we know the price of the 0 will be face value, say $100. We also know today's short rate, say 10%. So say the short rate will rise to 11% or drop to 9% with that equal probability. Thus, we can discount 100 we can discount 100 by 11% to get $90.09. And we can discount 100 by 9% to get $91.74. We take the average of these two equally probable prices, which is $90.92, and then we can discount the average one step further back by 10%, and we get $82.65. So with this model, we can value a zero of any maturity simply by extending our tree of short rates out as far as we need, and then discounting the zero at maturity all the way back to today. However, we need to find the correct short rates to use for the next year. From our previous example, we know today's short rate is, say, 10%. So we demonstrated how it would work if next year the rate went up to 11 or dropped down to 9%. However, these were just random rates that we used to demo the model. In reality, we can find what the short rates next year will actually be by matching the model's term structure here with today's market term structure. Sorry, this is the today's market term structure. So under today's market term structure, we see that a 2-year zero coupon Treasury bond has a yield of 11% and a volatility of 19%. So we have to solve for the actual short rates that will match the market yield of 11% and the volatility of 19%. So we start by relating the prices to yields. Here, today's price S is the 2-year zero's face value of 100, 2 years from now, discounted back by today. 2 years from now, here, Y2, discounted back to today here at the market yield of 11%. Next year's prices, S sub U and S sub D, is the same, just using next year's yield, Y sub U or Y sub D, and discounted 1 year less. Then we have to make a guess at the intermediate yields, Y sub U and Y sub D, which will satisfy two equations. First, the intermediate yields have to produce the prices, S sub U and S sub D, that discount back with today's short rate of 10% to equal today's price. And that would correspond to the market yield of Y2 is equal to 11%. Second, these intermediate yields, Y sub U and Y sub D, when entered into the volatility equation here, have to result in a volatility of 19%. So as mentioned earlier, the equation is based on the assumption that the short rate, is log normal with a volatility that depends only on time. So we can accomplish solving for the intermediate yields here using a computer program that will use all these equations to solve for the correct yields Y sub U and Y sub D. In our example, Y sub U and Y sub D turn out to be 14.33% and 9.79%. These become our 1-year short rates, R sub U and R sub D, which we will later enter into our rate tree. So to recap, we have just used today's market term structure to determine the correct short rates to enter into our rate tree for next year. So here's how the process of finding next year's short rates looks using the real numbers. We started with a 2-year zero's price at maturity, which we know to be the face value of 100. We just solved for the intermediate yields of 14.32 and 9.79%, which would result in intermediate prices of 87.47 and 91.08, which, when discounted at today's short rate of 10%, corresponds to today's price of 81.16 corresponding to today's yield for the 2-year zero of 11%. So simultaneously, the intermediate yields we solve for must result in a volatility of 19%. We can find the short rate out to 2 years, more than 1 year, in the same way. So 2 years out, we see that we have to solve for 3 short rates, R sub UU, R sub UD, and R sub DD. And we might be worried that we cannot solve for these 3 variables when we only have 2 quantities to match with, the yield and the volatility for the 3-year bond. However, because our model assumes that the short rate is log normal, with a volatility only dependent on time, we can apply the volatility equation here. We use the ratio of the rates in place of yields. The volatility at R sub U here equals the volatility at R sub D. So because the volatilities are the same, we know that the ratio of the rates 1 year out, R sub UU to R sub UD here is equal. So since these volatilities are equal, these volatilities will also be equal. So the ratio of R sub UD to R sub DD. Here they're set equal to each other. Cross-multiplying gives us this relationship. And once we solve for the 2 quantities, R sub UU and R sub DD, with our solver program, then we can find R sub UD by taking the square root of this product. So this is the full tree of short rates that we can find using this process, which matches the term structure that we're given. So given the market term structure and the resulting tree of short rates, we can now use the model to value a bond option. But first, we must find the value of the underlying treasury at the various nodes on the tree. Take a treasury with 3 years to maturity, a 10% coupon, and a face value of $100. This bond would pay $10 in the first year, $10 in the second year, and $110 in the third year. So the value of this bond is then exactly the same as the value of a portfolio of 3 zero coupon bonds, a 1-year zero with a face value of 10, a 2-year zero with a face value of 10, and a 3-year zero with a face value of 110. So at A, we have our short rate tree that can value all zeros according to today's yield curve here. At B, C, and D, we have our portfolio of zeros and their prices at maturity. We use the rates from the rate tree to discount the prices back each year to today. At E, we add up the prices of each of the zeros highlighted in yellow, the trees highlighted in yellow, to create one tree that represents the prices of the whole portfolio at each node of the tree. And then finally here at F, we subtract $10 of accrued interest, today's short rate being 10%, on each coupon date. So this F gives us our final tree of prices for the underlying treasury bond. Now that we have the prices of the underlying bond, we can value the options on it. Let's look at a 2-year European call, a European call meaning you can only exercise it at expiration. First, in 2 years, the prices of the underlying bond will either be 92.11, $96.69 or $100.22. The strike price of the call option is $95. So the value of the option will be the underlying bond's trading price minus the option's strike price. So if the bond is trading at 92.11 at expiration, the call value is negative, and thus it's worthless, and the call is out of the money. If the bond is trading at 96.69 at expiration, the call value is $1.69, and it's positive, so it's in the money. And if the bond is trading at $100.22 at expiration, the call value is $5.22, again positive, and also in the money. We use the same process for the 2-year European put. So again, in 2 years, these will be the prices. Strike price is still $95. But now the value of the put option will be the option strike price minus the bond's trading price. So if the bond is trading at 92.11, the put value is $2.89 and the put is in the money. If the bond is trading at 96.69 at expiration, the put value is negative and worth $0. The call is out of the money. And if the bond is trading at 122 at expiration, the call is again negative, worth $0, and out of the money. Sorry, the put. So now that we know the value of the options at expiration, we can use our old valuation formula to value the options all the way back to today. We have our short rate tree, which gives us the short rates to enter as R. We take the average of our two prices here off the node, take the average here, and then we discount them back to the node by the short rate. So we took the average of 0 and $1.69 here, gave us 0.74. We discounted it back by 14.32%, and we got this. Here, we took the average of $1.69 and $5.22, our prices, and then we discounted that average back by 9.79% and got $3.15. So then for the prices of 74 cents and $3.15, we take that average and discount it back one more year by the short rate of 10% to get the call value of $1.77. So we repeat the process for put options, and we end up with these value trees for both our calls and our puts. We can also value American style options, which are options that can be exercised at any time, using these value trees as well. And an American options value at any node will be the greater of either its value if held or its value if exercised. And to find the value if held, use the valuation formula to get the node's value one step in the future. And to find the value if exercised, take the bond price at a node, take the difference between the bond price at a node minus its strike price. So now that we have our underlying bond prices as well as our option prices, bond prices, option prices, we can easily calculate the option hedge ratios. So bond option investors want to see how much option prices change in response to changes in the price of the underlying bond. This relationship is measured by the hedge ratio. So once we have the hedge ratio, we can calculate the number of options we need to hedge our Treasury bond position. So let's look at the hedge ratio for a call 1 year from today. The hedge ratio is the difference between the possible prices of the call option 1 year from today divided by the difference between the possible prices of the underlying Treasury 1 year from today. So here's our call prices. Here's the prices 1 year from today. Here's the difference. Here's our Treasury prices. Here's our Treasury prices 1 year from today. Here's the difference. And then we take the difference in call prices over the divide by the difference in Treasury prices, and we get a call hedge ratio of 32%. So we get the call hedge ratio is positive because call prices increase when the Treasury price also increases, so positive correlation. And a hedge ratio of 32% means that for every dollar increase in bond price, there's a 32% increase in the option price. And the same process applies for finding the hedge ratio for a put 1 year from today. And we get a negative put hedge ratio of negative 0.17. And it's negative because, in contrast to the call prices, put prices decrease as the Treasury price increases, so negative correlation. And a hedge ratio of negative 0.17 means that for every dollar increase in bond price, there's a 17 cent decrease in option price. So in our model demonstration, our short rate had only course 1 year steps, Treasuries paid only annual coupons, and options could only be exercised once a year. But in order to get accurate solutions for option values, we need a tree with finely spaced steps between today and the option's expiration. Ideally, we would like a tree with 1-day steps and a 30-year horizon. That way, coupon payments and option exercise dates would always fall exactly on a node in the tree. And we would also like to have many steps to expiration, even for options on the verge of expiration. But at the time this paper was published in 1990, the author's computers didn't have enough memory to build a 30-year tree with daily steps. So even if the computers did have enough memory, it would take the authors hours to value a security. So instead, the authors built a sequence of short rate trees, each with the same number of steps, but compressed into shorter and shorter horizons, each tree with finer spacing than the one before. For example, they might use today's term structure to build short rate trees with a 30-year horizon, a 15-year horizon, a 7.5-year horizon, etc. And options, this way, no matter when the option expires, there's always one tree with enough steps to value the option accurately. So to accurately value an option on any Treasury, we would use 2 trees. A coarse tree with enough steps to value the Treasury accurately from its maturity back to today, and a fine tree with enough steps to value the option accurately from its expiration back to today. So we get the Treasury values on the coarse tree by using our old valuation formula. We interpolate the Treasury values onto the fine tree, and then we value the option by interpolating maturity, expiration, and coupon dates that fall between nodes to the nearest node. So interpolating across trees is both fast and accurate. Once we match the model values to the term structure, we can value options in a few seconds. The authors also considered how to improve the model. As we stated earlier, the authors felt that even though increasing the number of factors in the model improved results, it was too much harder to think about and it took far too much computer time. However, the author suggested that instead of tying forward mean reversion and forward short rate volatility together, vary them independently. The authors tried doing that, and it gave them very different results than when these two things were tied together. So they recommended using one or the other alone or a mixture of both in matching the term structure. 5. How did other researchers expand on this paper's contribution? Many other researchers extended this study, so here are 4 of the 8 that we found. Hall and White extended the BDT model by proposing other one-factor and multi-factor models, including trinomial trees. Heath, Jarrow, and Morton provided a multi-factor extension of the term structure modeling used by BDT. Longstaff and Schwartz extended the BDT model by incorporating a second stochastic factor that improved its ability to match observed interest rate movements. And Jamshedian expanded on BDT's one-factor approach using Gaussian interest rate models. So overall, other researchers might be extending the model by proposing multi-factor extensions or alternative distributions for interest rates. And then finally, is there anything left in the area still unanswered today? Some future work that would be great to explore for this model would be, first, with the access we now have to supercomputing and quantum computing, with some quantum computing capabilities available to the public via the cloud, could the author's ideal BDT model now be created, which would be a fine tree with a 30-year horizon? The authors previously said that their computers didn't have enough memory and that it would take several hours to get the prices. Now that we have access to much greater computer processing power and speed, could we create that ideal BDT model, and would it be economically worthwhile? And second, what are the possibilities for the BDT model in terms of AI or machine learning? How could the BDT model, be used in conjunction with machine learning techniques or other advanced computational methods to improve its accuracy or computational efficiency? So these are some areas that it would be really timely and relevant to explore.